Title of this lesson is I degrade, therefore I am, the impact of metabolic versatility on the industrial microbiology. The aim of this lesson is to illustrate how microorganisms have evolved a way to overcome problems caused by growth in suboptimal conditions, and how this peculiarity can be exploited for industrial applications. Cogito ergo sum is the famous, is the base of the philosophy of Cartesio, René Descartes, a French philosopher, mathematician and scientist of the 17th century. And this philosopher was saying that we are able to think, therefore this is something which is the base of our beings. Later on, in the 19th century, another philosopher, Feuerbach, was saying that we are what we eat. And in saying that, he was inspired by the studies of the Dutch physiologist Jacob Moreschot. And in general, he was saying that we assimilate what we have around us. So we assimilate what we have in the environment, not only food. In that period, which was during the Industrial Revolution, there was the idea that food, and indeed that was correct, that food was able to influence even the social status of people and the performance of the workers in the factory. If they were able to eat well and to have a balanced diet, they were able to perform better. Why we are citing these two philosophers? The reason is that microorganisms are not able to think, so they are more near the philosophy of Feuerbach, because they are capable of eating or degrading with high efficiency. So they can interact with their environment, and this is the most interesting part of the microbial world itself. By interacting with the environment, they can assimilate nutrients and they can produce byproducts. At the basis of their interaction with the environment, there is metabolism. What is metabolism? Metabolism is a distinguishing characteristic of all living organisms. Why distinguishing? Because we can distinguish different organisms also based on how they metabolize the nutrients. And this is particularly important in the microbial world, because the different microbes can be classified also based on their metabolism at the subspecies level. So in the same species, some can use a particular source of nutrients and some cannot. And this is a distinguishing characteristic. Small difference, so the conclusion is the small difference in metabolism can generate biodiversity. They degrade something different, they are different. In conclusion, metabolism, we can say that is assimilation of nutrients, transformation of the nutrients, and accumulation of byproducts. We can have in general two different types of metabolism. The first one is a balanced metabolism. In the balanced metabolism, we have a production of biomass, in general growth, and of simple byproducts, in example water and carbon dioxide. And we also have the excretion of potentially harmful products. So what is not used is excreted. When the metabolism is unbalanced, we have still the production of biomass and the excretion of simple byproducts, but we have also the production of other compounds. In one case, if we consider the human being, we have the accumulation of fat because we have too much food or we do not have the correct nutritional supplements, therefore we accumulate fat. But in the extreme situation, we can accumulate also something which is toxic for our organism and which can bring to health problems on the long term. This is extremely true also for microorganisms. So they can produce biomass in a balanced metabolism, and they can accumulate also some byproducts which are not harmful and which are used regularly. But if they grow in an unbalanced situation, rather than producing biomass, they accumulate byproducts, and among those byproducts we can find something which is extremely interesting for industrial production, as to be used as an industrial product indeed. In this picture you can see that industrially speaking we can take advantage of both types of metabolisms from microorganisms. In example, if we can keep a balanced growth in a yeast or in a lactobacillus or in a streptococcus strain, we can produce biomass, and we can use yeast for a bakery or brewery, and lactobacilli and streptococci for the dairy production, so for the treatment of milk, for the production of different products such as yogurt and cheese. On the other side, even more interesting is if we grow or we cultivate microorganisms in an unbalanced situation. In this case, the accumulation of byproducts by microorganism could also be extremely interesting, because among the products we can find several compounds of pharmaceutical interest, or compounds in examples such as polyalkanoates, which are produced by microorganisms and which are used as bioplastics, and so on. I will give you just a couple of examples of how unbalanced metabolism in microorganisms can produce something which is of interest for the economy and for well-being. In this first case, we see this beautiful orange microorganism. This is Actinoplanes teicomiceticus, which has been isolated around 50 years ago for its ability to produce an antibiotic. This microorganism, in a nutritionally balanced situation, is able to produce biomass. It grows very well, it can produce biomass. But if we unbalance its metabolism, we can force the production of an important antibiotic, which is teicoplanin. Teicoplanin is an antibiotic which was launched on the clinics in the late 80s and is still something of last resort, an antibiotic of last resort against methicillin-resistant Staphylococcus aureus. Why this microorganism is producing this complex molecule? Why is forced to produce this molecule? We have to say that soil microorganisms like Actinoplanes teicomiceticus grow in a carbon-rich and nitrogen-poor environment. Typically, they have an environment in soil where we have a lot of lignin, which is carbon-rich. In order to get nitrogen for their growth, those microorganisms should degrade a lot of carbon and extract nitrogen. The degradation of carbon brings to the accumulation of byproducts which are not used by the microorganisms and which could even result toxic for the microorganism itself. It is generally accepted that evolution has forced the assembling of those byproducts in something which is less soluble and less toxic for the microorganism itself. In this case, an interesting antibiotic. So, the microorganism has the double advantage of having toxic byproducts assembled in something which is less toxic, and also having something which has activity, killing activity against other microorganisms which are potential competitors in the struggle for life. Since we are dealing with an environmental relevant project, which is the Life BIOREST project, the second case study is reporting our observation on other microorganisms. So the question is, could microorganisms be used for something which is interesting for the environment? The answer is, of course, yes, because microorganisms can do almost everything. The important is to select them in the correct environment and to be able to grow them. So, if we want to look for an environmental application for microorganisms, we have two general aspects. The first one is the possibility that the microorganisms have to degrade or transform pollutant compounds. The second one is the possibility that microorganisms have to make the pollutant compounds bioavailable for themselves or also for other microorganisms. How microorganisms can make pollutants more bioavailable to themselves and to other microorganisms? In example, microorganisms growing in the presence of oil and in particular of contaminating crude oil or crude oil derivatives are able to produce compounds which are known as biosurfactants. Biosurfactants typically are amphipathic molecules which have a polar portion of the molecule and an apolar portion of the molecule. The polar portion could be formed, as in the case which you can see here in the picture, by sugars, while the apolar portion of the molecule can be a long acylic chain. Those molecules have the characteristic that they localize themselves at the interface between oil and water. Therefore, they facilitate the dispersal of oil in water, and the dispersal is done in a way in which very small droplets are formed, and these small droplets can be used by microorganisms in general. In our laboratories, we have isolated one Rhodococcus erythropolis strain, which of course, if we grow with a balanced microorganism, is able to produce biomass, but only a little amount of biosurfactants. While if we grow with an excess of oil, which means in an unbalanced situation, is able to produce biosurfactants. What is the advantage of those biosurfactants, which you can see here in the picture accumulated inside the culture medium? First of all, they allow the microorganism itself to localize inside oil droplets, which means that the microorganism is so apolar in its cell wall that is able to go inside oil rather than to stay in a water solution. From the other side, if we see the picture below, we see that by mixing oil, water and a microorganism or its biosurfactants, we can emulsionate the oil in water and we can originate very small droplets of oil which can be easily degraded by the microorganism itself. When we are dealing with a real application, mixing soil or contaminated water with oil doesn't bring any mixture of the solution, so you can see no dispersal of oil in sand, soil or water like in the right part in my right part of the picture. While if we add the microorganism, we can see that everything is mixed and therefore is better degradable by the microorganisms themselves. In a large-scale application, we have applied this microorganism for the bioremediation of the polluted side of Fidenza. The polluted side is polluted by hydrocarbons, and we want to remove the oil, so to create a situation in which microorganisms are able to degrade all the contaminating oil of the site in order to restore a healthy situation, healthy not only for the environment but also for the human beings surrounding the polluted site. In conclusion, why we use microorganisms rather than using other types of organisms to perform this task of degradation and production of metabolites? First of all, because microorganisms can be grown in balanced and unbalanced situation in simple laboratory condition and also in large scale. And their byproducts, which we can identify simply as waste, which is produced by them, can be used by the microorganisms themselves for assembling big molecules. But also the microorganisms are fast and furious, so they perform their task with high speed. You can imagine that a simple microorganism can double, so can reproduce every 20 minutes, which is something which is absolutely not possible in higher organisms. So they are very fast in growth and in the formation of their waste. Their waste can be assembled into a countless number of different secondary metabolites. So thousands of metabolites which are produced by microorganisms starting from their own waste products are thousands and thousands, and we don't know yet how many more we could find inside our environment. Of course, among those molecules, which are known as secondary metabolites, a lot of products of industrial interest are formed. How we can create an unbalanced metabolism, especially in the laboratory where we have to grow and to prepare our microorganisms and their products? Simply we supply an excess of nutrients in order to unbalance growth. Especially we point towards an excess of carbon compounds such as sugars or oil. In our company we have developed a database of culture media which are specifically designed to unbalance metabolism and who have an immediate industrial application, a cheap price and a good performance. In conclusion, I would conclude with this last paradigm. I degrade, therefore I am, is the real essence of the microbial world. So microorganisms exist and are identified based on their ability to degrade a lot of different compounds and to transform them into their biomass, but also into extremely interesting compounds. Thank you very much for your attention.